Hello everyone, and welcome to the final presentation for AAE 538 Air Breathing Propulsion here from Team C. To introduce the team, our 6 members are Alec Bosshart, Ali Saroya, Cole Nielsen, Benjamin Hooper, Kevin Wallace, and Peter Gegg. To go over our general design process, in the intermediate presentation we talked about determining our requirements and the kind of metrics we wanted to optimize in order to determine which design was working the best. We also picked out a few potential engine improvements at that time, but now here in the final presentation, we're going to actually determine the effectiveness of each of those improvements, iterating through with GasTurb alongside some outside programs like Excel and MATLAB, and then compile that information into a final engine design and set of recommendations. As a refresher from the intermediate presentation, these are the major design requirements for our engine. Starting from the baseline value that we were given and the target value, we will be modifying them to. The most notable ones here are the bypass ratio, the pressure ratio, turbine inlet temperature, and the change from a 3-spool engine design to a geared fan design. To start with this project, we began by matching the baseline engine that was given in the RFP in GasTurb in order to give us a validation point to make sure that we were doing a good job of modeling the engine as is before applying any modifications. The major parameters you see here are thrust and thrust-specific fuel consumption along with our efficiencies, all of which had an error below 1%. We attribute that error to the difference in GasTurb version. We were in 14, the RFP was in version 12. Other than that, we feel like this gives us a good baseline to start our designs. It has been validated with this baseline model, and we are good to proceed with our engine improvements. With this complete, we have our 3-spool engine design that matches the baseline architecture and its TS diagram, and now we have room to make our improvements, starting by turning this 3-spool into a geared fan.
So moving on to the geared fan model that we have, you see a picture there of the general arrangement of what the engine we've designed looked like without any further improvements besides the gear. The gear is necessary when going to a bypass ratio this large because it allows the fan to spin at a low speed while the intermediate compressor and the LP turbine can spin at a faster speed that are more conducive to their performance. Some characteristics of the engine that we've got here: the bypass ratio is 15, gear ratio is 2.5, the overall pressure ratio is 60. The HP compressor on this engine operates similarly to the one on the baseline engine, so its pressure ratio is still set at 5.76, and the rest of that pressure ratio is eaten up by 1.4 on the fan and 7.55 on the intermediate compressor. Turbine inlet temperature is 1930 Kelvin. The fan diameter is slightly increased to 3.45 meters on this compared to the baseline because of that increased bypass ratio. It gives a max engine diameter of 3.8 meters, and then the engine length, flange to flange, is from the front of the fan to the back of the LP turbine, is slightly less than the baseline at 3.57 meters. To optimize the baseline geared fan model, we ran some trade studies, the first of which was running the gear ratio from 2 to 5. As you can see in the plot, the lowest fuel consumption occurs at a gear ratio of 2.5, while we also get the maximum thrust, lowest total engine mass, and best LP turbine performance. This is the parameter that had the biggest impact of performance of the ones that we looked at. The next trade study we did was a look at the number of LP turbine stages. We varied this from 1 to 15, holding core flow constant. You can see on the plot there's a noticeable break at 7 LP turbine stages. The black line of specific fuel consumption starts to bottom out, where you get less benefit the more stages you go. The red line is overall engine mass, which continues to increase linearly with turbine stages. And then the blue line is thrust, and the gray line is LP turbine efficiency, both of which tend to plateau. So 7 LP turbine stages is kind of the sweet spot of maximizing our efficiencies while minimizing our weight. And then the last trade study we did here was on LP compressor tip speed. We varied that between 350 to 550 meters per second, again holding core flow constant. At 410 meters per second on the tip speed, we get the best performance, the highest thrust, the best LP turbine efficiency, and the lowest specific fuel consumption.
With the trade studies complete, a fully optimized geared turbofan model was created and run in GasTurb. This model incorporates many of the insights revealed by the trade studies, including a bypass ratio of 15, turbine inlet temperature of 1930, a pressure ratio of 60, and 7 LP turbine stages. The HP compressor, burner, and HP turbine from the baseline engine were all retained. A major benefit of the new geared turbofan model over the baseline engine is a significant reduction in thrust-specific fuel consumption and fuel mass flow. Fuel mass flow is reduced by more than 14%, and thrust-specific fuel consumption is reduced by more than 15%. Takeoff thrust is also slightly improved by almost 2%. By increasing the bypass ratio but retaining the baseline engine's core, this model produces a slightly larger and slightly heavier engine. The new geared turbofan engine was also compared to the baseline engine at cruise conditions. Here, we can see a less pronounced improvement over the baseline engine in thrust-specific fuel consumption, but still a large reduction in fuel mass flow. Thrust is also reduced at the cruise altitude and velocity, which is expected for a gas turbine engine. To complete the comparison to the baseline engine, a simplified mission analysis was conducted. It was assumed that both engines operated at cruise for the full duration of the mission. Cruising flight will dominate the duration of the mission for a long-range wide-body aircraft like the one our engine is intended to be flown on. Additionally, we are not provided any specifics about taxi and takeoff for our engine, so while this analysis is a bit of an oversimplification, it does highlight the benefits of a geared engine design. In this mission analysis, our engine consumes 14,700 less kilograms of fuel than the baseline engine over the duration of the mission. This is an improvement of almost 24%.
In addition to assessing the geared turbofan concept, we also looked at 3 major engine improvement concepts for further evaluation. The first one is fuel film cooling for the turbine blades, then interstage cooling in the compressor, and then recuperation of thermal energy from the exhaust into the combustor. Other parameters were adjusted to meet the engine requirements with these improvements, and we'll discuss those in the following slides. For the first method, fuel film cooling, as a recap from the intermediate presentation, the reason we decided to assess this was due to the improved heat capacity of fuel relative to air, as well as the advantageous cooling that comes from taking advantage of phase change. Additionally, we also want to take advantage of continued combustion through the turbine that would be potentially allowed by using film cooling. To contextualize the results, I'll give a quick overview of the flow physics that are relevant for liquid film cooling. There are 2 portions to liquid film cooling that are really present. There is the liquid film region, where cooling is dominated by phase change. And then after all of the liquid film is evaporated, we have a vapor region where, similar to air, cooling is dominated by insulation. For a first order feasibility assessment, we only looked at liquid only cooling, with the goal being assessing how much fuel is required to cover the entire blade in a liquid film. And to do this, we employed 1D modeling techniques similar to approaches used in analyzing rocket combustors. So our 1D modeling indicated that the amount of cooling flow that would be required to cool a single turbine stage, not the entire turbine, but a single turbine stage, is on the order of magnitude of the entire fuel consumption of the baseline engine, which is a very unpromising result. We could have assessed the effectiveness of vapor phase cooling, but the unpromising first order result that we have seen so far, plus the analytical complexity in predicting the insulation effectiveness of combusting fuel vapor, led us to ultimately dismissing this approach.
The next improvement to the geared turbofan we investigated focused on cycle improvements through the use of an intercooler and heat exchanger. Unfortunately, GasTurb does not have a model for geared turbofan with an integrated intercooler and heat exchanger. We instead modeled a 3-spool turbofan to match the geared version's thrust and thrust-specific fuel consumption as close as possible. One thing to briefly mention here is that GasTurb does not allow parametric studies of the recuperator effectiveness to show values of thrust, thrust-specific fuel consumption, etc. For this reason, we perform parametric studies on the combination of an intercooler and recuperator at the same time. This first contoured graph on the left plots the intercooler versus recuperator effectiveness from 0 to 1, with the contours representing the thrust-specific fuel consumption. The red contours represent a lower TSFC, while the blue represents a higher TSFC. It can be seen that only when the intercooler effectiveness reaches nearly 40% does it make a difference to the TSFC. Above this 40% threshold, increasing the recuperator effectiveness significantly reduces the TSFC down to 6.3 grams per kilonewton seconds. The graph on the right shows the same 2 variables, but instead the contours represent the net thrust. Increasing the intercooler effectiveness can be shown to increase the net thrust as well. The graph on the left shows the area where an improvement is made on the TSFC when compared to the 3-spool turbofan TSFC that was matched to the geared model. Only a very effective intercooler and recuperator can outperform the matched 3-spool turbofan. In an attempt to keep the thrust the same, we opted to vary the inlet corrected flow while still investigating the effects of the intercooler and recuperator. The graph on the left looks very similar to the previous graph and shows the TSFC versus intercooler and recuperator effectiveness. The graph on the right shows the value for the inlet corrected flow to match the same thrust as mentioned previously. Increasing the intercooler effectiveness appears to be the largest impact on decreasing the inlet corrected flow. And similar to the previous slides, the colored areas show improvements to the thrust-specific fuel consumption. I'd now like to pass it off to discuss changes in the bypass ratio in an attempt to improve the cycle performance.
As Kevin mentioned, we also looked at increasing the bypass ratio to attempt to improve our thrust-specific fuel consumption while also maintaining our baseline thrust. The logic behind this is that the air-to-fuel ratio is set in gas turb. So by increasing the bypass ratio while holding the maximum engine diameter constant, we're effectively reducing the mass flow of air through the core of the engine. So we're going to burn less fuel while achieving the same thrust as the baseline without the intercooler and recuperator. The contour on the left, similar to previous results, shows the heat exchanger and intercooler effectivenesses versus the TSFC. And the plot on the right shows the same two variables, but this time with the required bypass ratio to achieve our nominal thrust. As you can see, compared to previous results shown, we are much less constrained in the amount of heat exchanger effectiveness and intercooler effectiveness required to match our baseline TSFC. Or if we're still able to hit very high levels of effectiveness, we can further decrease the fuel consumption. Here are our improvement regions similar to before. As mentioned, these are much larger. The contour on the right shows that we're going to be looking at a new bypass ratio of approximately 18 to 20 to achieve the same baseline thrust. So as we've mentioned previously, we're going to need very high effectivenesses for both the intercooler and recuperator for any meaningful improvements on the cycle. Because component analysis of a recuperator and interstage cooling was beyond the scope of this class, we decided instead to look at research available to determine what typical effectiveness values are for these subsystems. One source that we found investigated intercooler effectivenesses on a range of 0.5 to 1 on a gas turbine power generation engine, indicating that an effectiveness of greater than 80% may be possible. Similarly, different papers showed that a typical range of recuperator effectivenesses is on the order of 80 to 90%, with one designed by Rolls-Royce being at 92%. These studies gave us confidence that these required effectivenesses is within the realm of feasibility. This led us to our proposed design. We showed that the bypass ratio increase is the most effective way to reduce thrust-specific fuel consumption, so we went with that. Without the specific component designs available, we assumed an effectiveness of 0.9, as discussed previously from those papers. Our previous slide showed that a bypass ratio of 19.2 would be required to achieve our baseline thrust of 411 kilonewtons. And once again, we'd like to reiterate that gas turb does not allow the analysis of an intercooler and recuperator on a geared turbofan. So this is on a 3-spooled turbofan with the intercooler and recuperator that has been scaled to mimic the geared turbofan. Our final outputs in gas turb with the aforementioned system show that we are maintaining the same level of thrust, but we've reduced our thrust-specific fuel consumption down to approximately 6.3226 grams per kilonewton second, and that's a decrease from roughly 6.7. And once again, this is with the increased bypass ratio at 19.2. And here we have a table comparing our geared turbofan model presented by Ben and Peter versus the geared approximation with the cycle modifications of an intercooler and recuperator. As you can see, our bypass ratio has increased, but our maximum engine diameter has decreased from 3.8 to 3.77. That is due to the aforementioned 3-spool approximation of the geared turbofan and not the geared turbofan itself. In reality, that would be the exact same at that 3.8. And once again, we have decreased our thrust-specific fuel consumption by roughly 0.4 grams per kilonewton second, while maintaining roughly the same level of thrust. So in conclusions, geared fan designs offer significant improvement over traditional 3-spool designs given competitive shaft masses, and that's why we're starting to see them enter the marketplace. We also found that fuel film cooling requires too much fuel flow to be effective in aircraft systems at this time. And finally, intercoolers and recuperators can provide benefits to engine cycle efficiency, but they need to be coupled with an increase in bypass ratio or other modifications that we were not able to explore. In this model, we did hold our total engine diameter constant while increasing that bypass ratio. Additionally, we need very high subsystem effectivenesses of the intercooler and recuperator for this to be worthwhile on implementing into the system. Thank you all for your time. We are available on Teams if anyone has any questions. Thank you.